100 components, right? How can I estimate the approximate posterior of Z1 and Z8? How can I do that? An idea? You can use empirical distribution, right? So if you have taken like statistics course before, we know that if you have like a bunch of identical distributed samples, right, you can construct empirical distribution on them. So what is empirical distribution? So suppose your this is a random variable z, right? Z could be a vector. I have like n samples, right? Then my posterior can be approximately by this summation of the delta functions. So this is the indicator function. This is basics of empirical distribution is defined like this. So for example, this is your true distribution, right? So suppose I use this distribution sample to generate a bunch of samples. So you can imagine that I will have very little samples here, very dense samples at high density regions, right? So I can use this bunch of samples to construct empirical distribution to approximate the original distribution. So how can I construct it? It's just an indicator function. Summation from all these n samples, and this is the indicator function. X equals to xi. Xi is I10. That's the empirical distribution. If you write down, it's actually a discrete distribution. Okay. So yeah, it will be something like this. Sorry, something like this. And if you first further partition the input domain into many bits and calculate the count, the ratio of the samples within each bin, it becomes histogram, right? The empirical distribution is just the finest histogram. You can partition it into like rough bins, right? And you can count how many points are inside each bin, and over the total number of samples, you have a ratio on that. So that's people often use to approximate the true distribution, right? My empirical distribution is just I do not use bins. I just use these indicator functions and just add them together and do the average. Does it make sense? Right. This is foundation of statistics, and it has many nice properties. Although this is a discrete distribution, but it has asymptotic convergence. It converges to the true distribution in terms of probability and also in terms of the distribution. I guess I have to look at the book, right? Different ways to do the convergence. But definitely, this empirical distribution has many nice properties, and in practical, it is good enough to approximate any complicated distributions. Does it make sense? Any question? Okay, so now the problem becomes, suppose I want to know the marginal distribution of only 3 components in your random vectors. Given this collection of samples, how should we do that? And each sample here, although I draw it in a one-dimensional space, right? You can imagine I use my Markov-Chain multi-column sampling and the sample in a high-dimensional space. Each sample is high-dimensional. Now I have like 1,000 high-dimensional samples, right? I want to approximate the marginal distribution of the 3 components in your random vector. How can I do that? For each sample, you just take off the corresponding 3 components, right? You have a sample for the 3 components. Like you have 1,000 high-dimensional samples. For each sample, you take off 3 components, you form a subsample, right? And then you merge this 1,000 subsamples together to construct another empirical distribution. That's it. Right? You never need to do explicit integration. Right? Or in other words, if you want to do that, you can do the integration over this empirical distribution that give you the exact same results. That's why it's convenient to approximate the marginal posterior over any subset of variables, right? Because you just take out the corresponding variables in your samples and use them together to construct an empirical distribution or a histogram. That's it. Does it make sense? And second thing, I want to estimate some interesting statistics or moments, right? So we usually represent some statistics or moments as a function of your random variable, say fz, right? So I want to know what is the expectation of fz or what is variance of fz. So even you have some approximate posterior distribution, say a Gaussian. If I give you a complicated function of your random variable, say sigma function, I want to know what's the expectation of that. We haven't discussed this before. It's intractable. We cannot compute it, right? And we use the numerical projection to do that. That's for a special case. If I give you another complicated form, and it's 3-dimensional, 4-dimensional. So f can be some 3-dimensional, high-dimensional stuff, right? If you want to compute the expectation of this vector of f, which is also a function of z, even you have some analytical form of q of z, the approximate posterior of z, your expectation is still difficult to compute, right? But now, if I have a bunch of posterior samples of z, how can I approximate the expectation of fz? An idea? Any suggestion?
Just take the average.
Yeah, you just evaluate f value, fz on each sample, z1, z2 to z, and I take average, right? So expectation is integration, right? Integration of fz and p of z and dz, right? So now this one can be estimated by taking average of the f value on a set of samples, right? As long as each sample follows this distribution. That's that's here where we write down, right? And also, a third important benefit is that with Bayesian inference, we can calculate predictive distribution, right? So predictive distribution is integration of your posterior distribution of the latent random variables and the predictive likelihood. You have computed the predictive distribution before, right? So as we know, like even I have some well approximation of this posterior distribution. If your predictive likelihood is complicated, just like a sigma, this integration is hard to compute. It's not analytical. But now with samples, how can we do that? Suppose I have a bunch of samples from this posterior distribution, Z1 to Z100, right? How can I approximate this integration? An idea? Yeah, you evaluate the predictive likelihood with each of those samples, and then take average. Because this is expectation. This is still an expectation of this predictive likelihood, right? So now to estimate this expectation, we can sample a bunch of, we can generate a bunch of samples of z, and then calculate this predictive likelihood and take average. So now it's pretty convenient actually. Why? Because in Markov chain, when it's called something's word, we're going to replace all the integration, right? All the integral with summation and average. Right? And we can prove that it's unbiased, right? Because each estimate is unbiased. Take average is unbiased, and take average can further reduce the variance. Right? This is a pretty good estimator, pretty good approximator to the things we're interested in. So now let me explain the advantages and disadvantages of Markov chain sampling. So far, what we have discussed is that some kind of advantages. We found out, okay, if we have like a bunch of posterior samples, it will be easier for us to approximate posterior margin of the posterior distributions, estimate any interested statistics, moments, or capture the predicted distribution. Other than that, Markov chain Monte Carlo sampling can guarantee asymptotic convergence to the true posterior. That means, like, in theory, as long as I always run this chain forever, and finally, all the samples you generate from this chain will exactly follow the true posterior distribution. This is different from variation inference or other kinds of approximate inference method like low-paid belief propagation. Those kind of methods is called deterministic approximation. That means there is always a gap between your approximate posterior and the true posterior. The Markov chain can remove this gap asymptotically. And compare with variation inference or other methods, Markov chain is really more robust to initialization. So basically, how do we run the chain? We just randomly generate the initial samples. Then we continuously generate more samples until convergence. So it's usually more robust, but it does not mean it is always robust. I have met a few situations that the chain is sensitive to the initialization, to the initial states of the random variables as well. And empirically, Markov chain works the best and often used as the gold standard to test other approximate inference algorithms. So as long as you have enough time, you have enough computational resources, you can use Markov chain sampling. You almost always get better results than other approximate inference methods. That's why, like, when I invent new approximate inference algorithm, we usually need to compare with some Markov chain sampling algorithms. And also, samples are more convenient to use than approximate distributions. Why? Because we never need to solve the integration. We always use summation. We use average to approximate the integration, which is much more convenient than explicit integration. So, of course, there's no free lunch. There are severe constraints of Markov chain sampling that make it not popular in practice. So, I mean, in practice, people rarely use Markov chain sampling. Why? The most important issue is the speed. So it's usually orders of magnitude slower than variation base. So some of my friends who focus on Markov chain Monte Carlo sampling told me that on average, like they try to use Markov chain Monte Carlo sampling to train neural nets. He found that, okay, I can get like 10% accuracy improvement, but I'm 100 to 1,000 times slower than variation inference and stochastic approximation. So in practice, people will rather sacrifice this 10% marginal advantages to gain, the speed. That's the key issue that people, especially in industry, people will never use MCMC. And a second thing is that although in theory Markov chain Monte Carlo sampling can guarantee convergence to the true posterior, but in practice it's a bit tricky to diagnose the convergence.
So it's clear to me how the Monte Carlo sampling works, but I cannot understand how we evaluate the Markov chain on the top of it.
You are what?
I kind of understand how the Monte Carlo sampling works, but I cannot figure out when the Markov chain comes in.
when the Markov chain come in.
Yeah.
Okay, when you have like sufficient resources, and you can get very accurate results because you're not gonna like, if you're doing wrong experiments, you're gonna like kill 1,000 people. I would rather wait 103 months computational time rather than some unreliable approximation. Actually, in many design and manufacturing scenarios that require your results must be reliable, must be accurate, then people will sacrifice time. And I would rather use supercomputers to generate results. I wouldn't use some like fast but cheap but inaccurate results. But with that being said, those kind of in that kind of applications, you have to be rich. You don't worry about money. You don't worry about time. Does it make sense? Any other questions? Okay. So another issue is that in practice, to diagnose the divergence is also an issue, right? Because there's no like theory tell you, okay, when you look at something, if it behaves like this, that means your chain has converged to the posterior distribution. I don't know when it converges. And also, there are a large amount of theory and showing that under this condition, under that condition, what is convergence rate. So it depends. But people have developed a bunch of like useful tricks to, and it's hard for parallelization. This is another way to prevent the large popularity of the Markov chain mechanical sampling. Why? Because even my computation is costly. If my computation can be separated and allocated to different computation units, I can still buy say a bunch of like 1,000 CPUs or deploy it on large clusters to accelerate, right? But Markov chain mechanical sampling essentially is sequential sampling, meaning that the new sample is generated based on previous samples. This is one by one, and the previous samples depends on the previous. Current sample depends on previous samples. So in general, it's hard to parallelize. Therefore, it's hard for large-scale applications. And another thing, the last problem is that it is easy to trap into single modes. So this is not only the issue of Markov chain. It's actually the issue of all the approximate inference vectors. So basically, if your true distribution is like this, right? You have two modes, and if you use Markov chain, if it jumps into this mode, so it's very hard for your sampler to jump off this mode to enter into this mode. So finally, you might end up a bunch of samples which can nicely approximate this mode, but the rare samples or insufficient samples to approximate this mode. Although in theory, what I can say give you enough time, like 1 billion years, you end up with arriving at this second mode and get all the true posterior. But in practice, we won't be able to wait that long, right? But this is not, it's not unique to a Markov chain mechanical sampling. If you use variational inference, your approximate posterior will very likely to trap in a single mode as well. So in the frontier research, how to scale up Markov chain mechanical to big data is a hot research topic. So if you have time to take a look at the talk given by David Dunson in the NeuroMIPS last year, he actually provided a few very interesting directions how to scale up Markov chain mechanical sampling to large applications. Okay, so now we have give a general description of Markov chain mechanical sampling. Now I want to introduce what's the basic idea. If I use one sentence to summarize all Markov chain mechanical sampling, what this sentence would be, right? So basically, Markov chain mechanical sampling samples a sequence of variables using a Markov chain, such that this sequence of samples will converge to the desired posterior. So you can consider like I start with Z1, the first random variable, right? And given Z1, I sample Z2. This is a traversal through a Markov chain. And Z2 to Z3 until Zn plus 1. And so the generation of each sample is Zn plus 1 from some conditional distribution, P of Zn plus 1 given Zn. And we have guaranteed that the marginal distribution of the sample is converging to the true posterior distribution. That's the key idea of the Markov chain. And Markov chain Monte Carlo. And from this procedure, you can see that the samples are strongly correlated. Why? Because you sample each example is Zn plus 1 is from conditional distribution. Depends on the previous sample Zn, right? So, given after Markov chain, the chain is actually determined, the status of the chain is actually determined by, first, the initial distribution, the distribution of your initial random variable, Z1. And second, we call it transition kernel. So what is transition kernel? It's actually the conditional distribution you give this current sample to generate the next sample. So I will frequently use the word transition kernel, but don't be confused here. It's just a conditional distribution to generate the next sample. And we denote the transition kernel is like this, like Zn to Zn plus 1. And given your initial state or initial distribution of the Markov chain, and also the transition kernel determines how you transit the states, you can identify the final states of your Markov chain and also all kinds of behaviors of your chain. Right? So the development of Markov chain Monte Carlo sampling is the art to design the transition kernel. Because in Markov chain Monte Carlo sampling, we do not care much. We do not care the initial very much. Why? Because I want from arbitrary initialization, finally my random variables the distribution of my random variables will converge to the true posterior. That's why we do not care much. And we want to build up special Markov chains to always converge to the true posterior. So now we want to say, like, in general, what distribution does a Markov chain converge to? Right? So such a distribution is called an invariant distribution. So basically it says, okay, in my Markov chain converges, right? So my current status, the random variable follows some distribution. And then after I converges, I jump to the next status, right? My distribution of this next random variable will not change. Remain the same as the previous, the distribution of previous status. Then we say, okay, this Markov chain converges. And this distribution is called invariant distribution. Why? Because when I jump into the next state, the marginal distribution does not change. That's why it's called invariant distribution or stationary distribution. Does it make sense? Right? So how do we express invariant distribution? We denote the invariant distribution by like P star, right? So it means, okay, if I have arrived at the invariant distribution, then I use this invariant distribution to sample any standard Z prime, and use my transition kernel to sample the next state, P of Z. And it turns out that the marginal distribution of Z is still this distribution, P star of Z. And this marginal distribution of Z can be computed by the marginalization of this drawn distribution of P of Z prime and Z, right? So this is actually the drawn distribution, starting from Z prime and transit from Z prime to Z. This is a conditional distribution, right? As we just mentioned. So when you starting from any distribution, right? You can multiply with the transition kernel to calculate drawn distribution of the current sample and the next sample. And then you do the marginalization, you obtain the marginal distribution of the new sample, right? But invariant distribution means that, okay, after marginalization, I recover my original distribution. This is called invariant distribution. And we claim that this P star is invariant to the transition kernel T. So basically it means, okay, the inverse is not some like isolated concept. It must be associated with some transition kernel. Right? Some distribution, we say is invariant station distribution, it must be with respect to some particular transition. Obviously, we want to design the kernel to which the target posterior is invariant. Right? I want my target posterior is invariant to the transition distribution. That means, okay, when I run my Markov chain, I finally will converge to this true posterior. That's the key idea. Key idea of design our MCMC algorithm is to define or design some Markov chain whose the target posterior is invariant to the transition kernel. How do we design a transition kernel? But to find out that transition kernel, we need to examine the invariance. Right? We need to ensure that when I propose a new transition kernel, the true posterior is invariant to this transition kernel. Otherwise, the chain is useless, right? Then that refers to an important problem: how can we examine invariance? And from the definition, we need to do this marginalization. Right? Multiply the current distribution with the transition probability and marginalize, and we see the marginal distribution of the new sample, whether it is consistent with the original distribution. Right? But that requires you to do marginalization. It's very hard. Again, as long as you involve integration, it's very hard. So in practice, we often use a sufficient condition to examine the invariance. It's called detailed balance. So remember, this is a sufficient condition. It means that, okay, if your distribution satisfies the detailed balance with respect to some transition kernel, then I can conclude that your distribution is invariant to this transition kernel, but not vice versa. Like if your distribution is invariant to the transition kernel, it does not necessarily satisfy the detailed balance. But practically, this one should be sufficient. I just construct some transition kernel such that they satisfy this detailed balance. Then I can safely use it. Does it make sense? So what is detailed balance? Basically, as long as you can prove that for arbitrary two states, z and z prime, if you can show that your distribution p star of z multiplying with transition probability from z to z prime is the same as you start with the z prime and multiplying with the transition from z prime to z. So basically, the probability you start with this target distribution and then jump to the another state. It's the same as you start with the distribution from another state and jump back. If the two probabilities are the same, we say, okay, this target distribution and the transition kernel satisfy the detailed balance. Then we can claim that this distribution is invariant to the transition kernel. Does it make sense? So that's the way I memorize the detailed balance probability as I jump back. It's called detailed balance. So how does detailed balance lead to invariance? Right? I want to give you a simple proof because it's really, really straightforward. So remember, if you want to show that the distribution is invariant to the transition kernel, you want to calculate. Say if you start from any space z, right? Any random variable wz, right? When I jump to the z prime, I have this joint probability, right? P of z and z prime. Now I want to check what is the marginal probability of z prime. That means I have to marginalize off z. So I have to do the integration here, right? So I want to see whether this marginal distribution, P of z prime, let me denote the distribution I want to check is by P star. So according to the definition of the invariance, if I use P star to sample Z and use Z to generate Z prime, the marginal distribution of Z prime should be also follow P star, right? So now I want to check this one, right? So according to the detail balance, starting from Z and then jump to Z prime is the same as starting from Z prime, jumping from Z prime to Z. Right? This is detail balance. So I can just replace this product by this product, right? And then integrate over Z. So what's the result? So first, Z prime is constant, right? Because in this integration, I'm just integrating Z, right? So I can move the Z prime, P star Z prime outside. Then the integral has this transition kernel from Z prime to Z and to the integration, right? So what's this integration? What's this? Transition kernel is a conditional probability, right? So this is actually the conditional probability of Z given Z prime, right? So just integrate out the conditional probability, what's the result? Just one, right? This is just one. So that means the marginal distribution of Z prime is simply P star. First, use your target distribution P star to sample some variable Z. And then, condition on Z, I generate a sample Z prime, right? Now I want to investigate what's the marginal distribution of Z prime. I do it. So suppose we satisfy detail balance, I do it, I found, okay, the marginal distribution of Z prime also follows P star. So that just means, okay, after doing this transition kernel, my marginal distribution of the random variable does not change. Z variable. Any questions? And here you can test with arbitrary distribution P star, right? Only when this satisfies, we can say P star is invariant to the transition kernel. If it does not satisfy, you cannot state that point. So don't be confused here. So Z can be arbitrary random variable. It does not necessarily to follow P star. I'm just saying, like, if I use P star to sample some random variable and then use some transition kernel to generate a new random variable, and then under this probabilistic modeling, if I calculate the marginal distribution of Z star, if it still follows P star, then I say, okay, this P star is nice properties, is invariant to this transition kernel. So don't be confused here. Like, you can do not assume like Z must satisfy P star. It's just a tool to check whether P star kind of match the transition kernel. So, as we mentioned, like, this is just a sufficient condition, meaning that, okay, if some distribution and a transition kernel is satisfied detail balance, then the distribution must be invariant to the transition kernel, but not vice versa, right? So, a Markov chain whose stationary distribution and the transition kernel respect detail balance as reversal. Why? Because you say the detail balance just says, okay, I start from Z and jump to Z prime has the same probability that I start from Z prime and jump back to Z, right? So why? This is why it's called reversal. Reversal is just some sufficient condition to show the invariance, right? But if some chain I still satisfy some kind of invariance, it does not necessarily mean it's reversible. So now, if another thing we should be concerned is that a Markov chain can have multiple stationary distributions, meaning that it can converge to different invariant distributions. This is possible, right? It depends on how you choose the initial distribution, right? Different initial distribution might lead to different stationary distributions, right? So this is obviously not what do you want, right? I do not want I start from this initialization, it converges to the true posterior, and then start with another initialization, it jumps to another different distributions, very, very different from my target. It's not what I want. So in our algorithm design, we want Markov chains only converge to the desired posterior, no matter what initial distribution is chosen. The question is, does such kind of Markov chains exist? Yeah, this kind of chains is called ergodic chains. Or it's probably called ergodicity. So an ergodic Markov chain only converges to one invariant distribution or one station distribution. They're basically the same thing. So I'm not going to introduce what is the rigorous definition of the ergodic chain. Just give you some intuition or conceptual idea of that. So informally, in an ergodic chain, it is possible to go from every state to every state. That means, okay, my probability to jump to any state to another state is non-zero. So imagine like your random variables can choose like, can take 100 possible states, or even can take like infinite number of states, right? So just as, okay, starting from any state, it can jump to a different state or the same state. And also, the probability that you left from one state and never come back is 0. So this is kind of a weird thing, right? If you start from one variable, say taking the value to be 3, right? And then you run a chain, it is possible that your random variable will never be able to be 3 again. But that's not ergodic. But anyway, we're not diving into the details about Markov chains because there are 1,000 properties about them. When I study this kind of topic, I always got confused about this ergodicity and periodical and whatever. It's many concepts, but just be aware of these two key properties. First, reversible, second, ergodicity. So an ergodic chain is also called irreducible. So what is reducible? Reducible simply can be like if I look at all the possible values your random variable in your chain can take, like I can partition them into subgroups. Say in this group the random variables can take 1, 2, 3, and another group 4, 5, 6. And reducible means that okay, my chain, if my chain sample random variable whose value to be some value inside this subset, it will never jump off. It just take values 1, 2, 3 alternatively, or whatever, but we'll never be able to jump to the value to be 5. It's called reducible. Or you jump into this subset and never be able to jump back. This is called reducible. And irreducible means that okay, it will never gonna happen. Like even I enter into this group, I still have non-zero probabilities to jump into this group and to go to traversal 4, 5, 6. This is the idea. And ergodic chain is also called irreducible. Now it's more clear, right? So I will be able to traverse all possible states in the whole sample space rather than trapped into some local subset. So the invariant of stationary distribution of an ergodic chain is called the same thing. Equilibrium is also a stationary distribution, but it's just from some ergodic chains. So in Markov chain when we call something, our stationary distribution is always equilibrium because we're always trying to construct an ergodic chain. Because we want to ensure that it only converges to one stationary distribution. So to summarize, in Markov chain Monte-Carlo sampling procedure, the invariance guarantees that your samples will finally converge to the true posterior, namely your empirical distribution is unbiased. And ergodicity guarantees that your sample space can be fully explored rather than partially. I suppose this is your true posterior distribution, right? I want to generate samples across all the input domain, right? Rather than just restrict it into this small mode, right? And then I can only cover this part. This is not what I want. Right? And but how can we identify the probabilistic? This is not very trivial. Unfortunately, commonly, if we design a homogeneous Markov chain, is usually the algorithm, which is subject only to weak restrictions on the invariant distribution and transition curves. So that means, like in 99% of practical cases, you can just assume your chain is algorithm, as long as you are doing homogeneous Markov chain. Oh, I didn't mention the homogeneous, right? So what is homogeneous Markov chain? So it basically says the transition kernel has nothing to do with the current step. If it is a function of n, it's called inhomogeneous. Like if you use a Gaussian to transit Zn from 0 plus 1, you know that whatever is Zn and 0 plus 1 theory is just the same distribution. The parameters does not depend on n, right? It's homogeneous. But if your parameters depends on n, like step 1, you have the mean to be 0, whereas to be 1, and step 2, you have a mean to be 1, whereas to be 2, then it is inhomogeneous. The inhomogeneous is kind of weird, so people practice always use homogeneous Markov chains. So, in general, our sampling procedure consists of 2 stages. First, it's called before burning, and second is called after burning. So what is burning? Burning just means, okay, you have your chain has converged to the true posterior. So before the burning step, it just means, okay, your chain has yet converged to the invariant distribution, and in practice, we usually set up the maximum number of steps before the burning, and also use a variety of tricks to verify the convergence empirically. Like, look at the trace plots. What is trace plots? You just look at several random variables in your samples, right? Each sample could be a random vector. Just pick up a few of them and calculate their empirical distribution and look at their curve. If their curve turns to be stable, and then you can claim that, okay, very probably they have reached the burning state. Otherwise, I have to wait. Again, this is just ideal status, right? In practice, I will never be able to guarantee it. Okay, it has already arrived at burning state. So you just use some empirical heuristics to determine whether I have arrived at burning. And then after burning, the Markov chain has converged, and then we generate posterior samples. We assume, okay, from this status, Markov chain, every samples generated by Markov chain will follow the true posterior, right? So next, we're going to harvest those samples. How can we harvest them? As we just mentioned, the Markov chain, the samples generated from Markov chain are highly correlated, right? Because Z1 depends on Z2, Z2 depends on Z3, right? So we need to reduce the strong correlation. How can we do that? We often take every nth sample. I'm not going to take in consecutive samples. I'm going to take every few samples, like every 50 samples, every 10 samples, to reduce the correlations. And again, this does not guarantee that finally your correlation is 0. And also cannot guarantee independent, because even 0 correlation does not mean independent. So to measure that, how many your current collection of the samples correspond to how many independent samples. There's an important metric called effective sample size, ESS. This is when you just use any like Markov chain recall sampling package, they very probably provide you a measure of ESS to see how many actual independent samples correspond to the current samples. Like suppose you have 1,000, you have collected 1,000 samples, but effective sample size might be just 20. And it just means, okay, if I convert your 1,000 correlated samples into independent samples, how many independent samples they're equivalent to? It's just 20. It's too little, right? You have to, too few. You have to collect another probably 10 10,000 samples. And again, like effective sample size has a rigorous formula, and it's not feasible to compute. So people usually use some approximation or estimation to calculate effective sample size. So these are all about the physics of the Markov chain, Monte-Carlo sampling and Markov chains. Any questions so far?
So suppose we choose the m to be 10 instead of 5. Does 10 guarantee like lower correlation compared to when m is 5?
Yeah, of course. But it does not mean like they have a huge difference. It depends on how you define the transition kernel. I can give you a very easy transition kernel. That is tx1 to x2 is just x1. So what you sample is just x1, 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 x1. Always x1, right? That means in that case, like you take every 5 samples, you take every 10 samples, doesn't matter. That's why we have to compute the effective sample size practically. So if I, what's your question?
So I guess why is the goal to reduce the correlation between?
If suppose I want to estimate some statistic, right? It's a function of x, right? So if I'm collecting a bunch of samples, say x1, x2 to xn, right? So as we mentioned before, right? We can use Markov chain Monte-Carlo sampling. We can just do the average. Right? So I'm gonna calculate the summation of the f value on each sample and take the average, right? So mention that this is unbiased estimate because if you take expectation, it will converge to the expectation of fx, right? But the issue is that how accurate of this expectation, and how can we evaluate the accuracy? An idea? How can you evaluate the accuracy? So remember, this is a random variable, right? So suppose this is your true expectation of this fx, right? So I use this one to approximate this one. This is just a random variable, right? That means on average, it will converge to this. It's called unbiased, right? But for each particular approximation, it could be here, it could be here, it could be here, it could be here, right? And what kind of measure can tell us how far away your heard that variance, right? So if you compute the variance of your estimation, right? If this x1, x2 to xn are independent, you know that it is a square root of n, 1 over square root of n of variance of your samples, right? Your f value over each sample, right? But this only based upon x1, x2 to xn are independent. If those samples are not independent, you cannot use this estimation. Why? Because you have to account for the correlations. So there is a formula to square root of n of variance. But you have to calculate pairwise correlations between those fx1, fx2, fx1, fx3, and etc. Right? So unless the smaller the correlations you have, the smaller of the total variance you have. That means more accurate your estimation will be. Does it make sense? Any other question? Okay, so now we'll introduce the first Markov chain sampling from Metropolis Hastings algorithm. It's a general framework for Markov chain some green. So, so what is metropic system? The idea is as follows. So in each step, I'm going to use a proposal distribution to generate a candidate sample. And then I will introduce some mechanism to decide whether to accept this new sample or not. That's the idea, right? I use some whatever things to generate a sample. And then I test whether I should preserve the sample or just throw it out. We denote the proposal distribution. Remember, the proposal distribution is not the transition curve. It's just some distribution to propose the candidate samples. By this Q of Z prime gives Zn, Z prime is a candidate sample. So commonly used proposal distribution is a Gaussian distribution. Given the current sample Zn, I want to propose a candidate. So I sample Zn. I sample Z prime, this candidate, from Gaussian with mean to be Zn, the variance to be sigma square, right? So you can imagine this is Zn, right? So Z prime is generated along this way, randomly. And then I use this proposal distribution to generate candidate Z prime first. And then I accept Z prime with a probability which calculated in this way. So probability is a minimum of 1 and this fraction. And the denominator and the numerator is actually the probability to start from Z prime and jump back to Zn, use your proposal distribution. And the denominator is you start from Zn and jump to Z prime. It's kind of similar to the detailed balance, right? But remember, detailed balance is talking about the transition. This is not transition. This is just proposal distribution. We can construct transition curve later, right? Based on this. This is not transition. It's just a proposal distribution. So basically, I will to determine whether Z prime is going to be accepted or thrown out. I first compute the probability that Z prime with the data. This is actually the drawn probability of your model. And then multiply the proposal probability from Z prime to sample Zn. Then you divide this product by the drawn probability of Zn and your data. And then the proposal probability from Zn to Z prime. And of course, this probability must be less than 1, right? That's why we should choose a mean value. Mean 1 in this fraction. So in practice, how do we implement this? Right? How do we accept Z prime with this probability? We use a uniform random variable. We just sample the uniform random variable between 0 and 1, and then test whether it will be less than this probability. If it's less than or equal to this probability, then we'll accept Z prime. Otherwise, we'll throw it out. Does it make sense? Right? And also, to ensure the numerical stability, I'm going to take logarithm first and then take exp, so that I will not need to divide two very small things, right? So probability are very small. If you divide one number which is close to 0 by another number close to 0, it's very easy to get numerical issues. That's why I'm going to take a logarithm first and then take the exp. So the logarithm first is log 1 is 0, right? And logarithm of this is just log summation and subtraction. So if it turns out that we accept Z prime, then we'll assign Z prime to be our next state, Zn plus 1. Otherwise, I will set Zn, the current sample, to be the next. So basically, if I have a Z prime, right? So this is Zn, right? So for Zn plus 1, if I generate Z prime from Zn, I found it is useful, and then accept it, I just assign Zn plus 1 to be Z prime. Otherwise, I just assign Zn plus 1 to be Zn. That means I duplicate the sample. So that means that the chain may contain many duplicated samples due to the rejections. And that's some kind of things which are interesting and worth your notice. So before we give the proof, what's the any question regarding the sampling procedure? I think it's pretty straightforward.
So the idea, okay. So the idea is that we use can you go back a slide actually? So like we use the ratio of the
joint probability.
Right, the joint with the new sample and the old sample. And essentially this is saying, so if the numerator is bigger than the denominator, then it'll be greater than 1. So essentially like, or kind of like saying like, if our next guess for z prime is kind of like worse than zn, then we kind of throw it away.
Yeah.
And we just use the same.
Yeah.
Okay.
That's just under some probability.
Okay.
Yeah,
Under
because,
some probability.
because you need to traverse the whole sample space, right? Also including the low density regions. So that means, okay, even like my joint probability is not increased, right? It's not increased. So this one is just 0.8. I have a large chance to be preserved as well.
A large chance that you will.
I mean, to accept this new sample, even if it's in lower density regions.
Okay.
Any other question? So basically, just every step to generate one sample, I just do two things, right? First, I'm going to use some proposal distribution like Gaussian to generate one candidate, and then I test whether I'm going to accept this candidate or not through this probability. And to implement this is pretty simple. I just calculate this probability and then generate a random uniform distribution to say whether it is less than this probability. If this, I keep this. Do you have a question? Okay. Any other question? So now I want to prove this algorithm is correct. Why is this correct? To prove that, it's simple. Just show that metropic histine guarantees the detail balance. So if it guarantees the detail balance, that means okay, your posterior is invariant to your transition kernel, right? And then that means your marker chain will converge to the true posterior, right? Of course, right now we assume the transition kernel is homogeneous, and in most cases it's just algorithm. You don't need to worry about it converges to different distributions. So how to improve? Metropolis histine satisfy the detail balance, right? So we need to recover this transition kernel. So remember, the proposal distribution is not transition kernel. The transition kernel is the probability that you jump from this to that, right? The proposal just gives you a candidate. You have to also account for the probability to accept it or not. You need to combine them together to construct a transition kernel, and then see whether it satisfies the detail balance, right? So, given that arbitrary Zn and Zn plus 1, which means that two states in your chain, right? Consecutive states in your chain, right? We consider two cases. First, Zn plus 1 is not equal to Zn. What does that mean? Yeah, that means Zn plus 1 must be a new sample, right? It must be generated from your proposal distribution and then be accepted, right? So let us first consider this case, right? So Zn plus 1 must be obtained from accepting some proposal, right? And then let us calculate the transition probability, right? So the transition probability from Zn to Zn plus 1 is actually the probability that your proposal distribution generates Zn plus 1 first. And then it is accepted, right? The probability of these two events. First, Zn plus 1 is generated by a proposal distribution. And second, this new proposal is accepted. Right? That's why we need to multiply together to get the transition kernel, transition probability. So then let's just take a look at this, right? So if you divide the fraction, on both numerator and denominator by your marginal distribution of the data, so this becomes the posterior distribution, right? So that means it doesn't matter, right? As long as accepted, then the posterior distribution will satisfy this constraint swap. remember when we say the D2 balance, we want to prove that your posterior distribution and your transition kernel satisfy D2 balance. Then that means the posterior distribution is invariant to your transition kernel. Then the posterior distribution will be converged by, the Markov chain will converge to the posterior distribution, right? So from a computation perspective, you divide both numerator and denominator by this constant. It doesn't matter, right? It's the same, exactly the same as you do not divide that. So now, if you divide both sides by this P of D, you have this posterior distribution of Zn plus 1 given D in the numerator, and the posterior distribution of Zn given D, right? And then you multiply this transition proposal probability. So now, this is a transition kernel, right? To test the D2 balance, we need to test the product between your target distribution, which is posterior, with the transition kernel. Right? So the transition kernel, we have just arrived. We just derived this. This is the product of your proposal probability and this acceptable probability, right? Now you multiply with the posterior P of Z and D. So you end up with this form. So now what can we observe from this product? So you can see this product is the same as the denominator, right? So the numerator is that I start with Zn plus 1 from the posterior and then jump to Zn from my posterior, from my proposal distribution, right? And numerator is that I start from Zn from my posterior and then jump to Zn plus 1, right? And the numerator is actually the same as the terms, the product terms outside. And then I can multiply this product into the mean. So now I have a mean of product from starting from Zn to Zn plus 1, and the product of the probability starting from Zn plus 1 to the Zn, right? So now it's kind of symmetric. So this is one side of your D2 balance, right? Now I want to say, like, if I starting from the new sample and then jump back to the previous sample, what is the probability? Right? That will be the posterior probability of Zn plus 1 and multiplying the transition probability from Zn plus 1 to Zn. Right? You even do not need to derive this. Just replace the subscript. You end up with the same thing. Right? But this one is symmetric, right? So you replace Zn plus 1. We replace Zn by Zn plus 1, replace Zn plus 1 by Zn. You just switch the two products to the mean, right? So they are exactly the same. Does it make sense? That means these two probabilities are the same, so they satisfy the balance, right? So, of course, we have a polar case that what if Zn plus 1 is exactly the same as Zn, right? That will include two situations. First, you sample a new, you generate a new candidate, but you're rejected, so you keep Zn. Or you generate Zn plus 1. You generate a new sample, and this new sample is exactly the same as Zn, and is accepted. So that means your transition kernel has to consist of two parts. First, your probability that you reject the proposal. All the probability that your proposal is Zn plus 1, which is the same as Zn, and also accepted. And then you can multiply with the corresponding probability, like posterior of Zn given D multiplied with the transition probability from Zn to Zn plus 1, and to calculate them. So because Zn plus 1 equals to Zn, so you can see in the outside, they are the same. They are both the posterior probability of Zn given D, right? And the inside, remember, you reject proposal from Zn, right? You generate a candidate from Z n and then reject it. In both cases, that means this rejection probability is the same. And second, your proposal is the same as Z n and then accept it. It's just like, okay, I sample Z n to Z n and accept it. They are the same, right? So then that means, okay, these two probabilities are the same. Conceptually, you can also consider it like my standard is Zn, right? So my next standard is still Zn. So the probability that I start from the posterior of Zn and then jump to Zn is the same as the probability I start from Zn and jump to Zn. The same thing. This is a simple color case. So and by summarizing the two cases, we show that metropic histine satisfies P2 balance, and also because we use homogeneous chains, in most cases they're ergodic, then they will converge to the true posterior. And if your proposal distribution is symmetric, like Gaussian distribution we just mentioned, we will switch Z and Z prime here, it doesn't change probability density. Then we will do the calculation of the accept probability. You can see that this Q of Z, this proposal distribution will cancel them because they are same. Then that means to calculate the accept probability, you only need to calculate the ratio of the model, joint model probability or likelihood. And this is called Metropolis algorithm. So actually, the invention is kind of in a different order. So the Metropolis algorithm was first invented, and then comes the metropic histine. So metropic histine is kind of an extension or correction of metropolis if I use like a non-symmetric proposal. And it is interesting that in the metropolis algorithm, I mean, if you use symmetric proposal description, if your proposal increases the model likelihood, this fraction is always bigger than 1. That means your accept rate is always 1. That's interesting, right? So that means, okay, if I have a sample here, and if I generate a sample here, I increase the model likelihood, right? Then I'll always accept this. So actually encourage you to accept more high density rigid samples. Any questions so far? Okay, we'll stop here. And next Monday, we'll explain what's the problem of the metropic histine algorithm.